Welcome to lecture 42 on essentials of topology. Continuing from the previous lecture, herein first we will discuss the connectedness of some of the subsets of R2 and thereafter we will study the well-known intermediate value theorem. Begin with what we have seen in the previous lecture, that unit circle is connected. Let us see in the example. We are taking here again the circle. This is C, which is collection of all ordered pair x, y in R2 such that x minus a whole square plus y minus b square is equal to r square. This is a general equation of the circle with standard topology as a subspace of R2, and we can also show that this is connected. So when we are trying to show that this circle is connected, let us define a function f from this interval. Let us take this closed interval to R2 such that f of t is equal to a plus r cos t and b plus r sin t. Actually, this function it can be defined as a combination of these two functions. The first one is f1 is from this closed interval to set of real numbers r such that this f1t is equal to a plus r cos t, and the second function f2 from this closed interval 0 to 2 pi to set of real numbers r such that f2t is equal to b plus r sin t. Note that both f1 and f2 are continuous, and therefore this f is also continuous. And if this f is continuous, let us find the image of this interval, and that is nothing but this set C. And how this is set C? This is simple to justify, as this C is continuous image of this interval 0 to 2 pi, and note that this is connected. We conclude that C is also connected. Similar to the example of this circle, let us take another example, that is the example of parabola, that the parabola which is given in the form of a set. Let us take this set is P. This is collection of all elements in R2 such that y square is equal to 4ax with standard topology as a subspace of R2 is also connected. If we want to see the connectedness of this parabola, let us define a function f from R to R2 such that f of t is equal to t square upon 4a t. Just like the previous case, we can conclude that this function f is continuous. Also, what is the image of this r? That is f of r is nothing but that is parabola, and it can be seen from here too that if we are taking this is the parabola y square is equal to 4ax, every point can be given on this parabola as t square upon 4a t if we are taking this as t. As this is connected, note that function is already continuous, so we can say that this set P, this is also connected. Therefore, the parabola is a connected subset of R2. Let us take the next example. This is the line which is a subset of R2, what we can show that this line is also connected. So we are talking about the connectedness of this line, which is y is equal to ax plus b. Let us take this set as L. Now define a function f from set of real numbers to this R2. This function is defined as f of t is equal to, this is t and at plus b. Now what about the image of R, that is nothing but L. Again, because this f is continuous, which is defined here, this f is continuous, and we know that this R is connected. What we can conclude that this is also connected. Why? Because the same region which we have used, this is a continuous image of a connected set. Moving ahead, what we have shown that the line is connected. Let us take another example that is inspired from the previous one. If we are taking the union of two sets, the first one is collection of all ordered pair in R2 such that x is equal to 0, and second is take all those points in R2 such that y is equal to 0. With standard topology as a subspace of R2, we can justify this is also connected. If we want to see what this set is nothing but this is y-axis. What about this set? This is nothing but x-axis. So what precisely we are saying, that is union of x-axis and y-axis is connected. And if we want to see it, it's simple one. Let us take, okay, this is our x-axis and this is our y-axis. We have already justified that lines are connected. So let us take this is line L1 and this is line L2. So here L1 and L2 both are connected. And one more thing is here, that L1 intersection L2 is non-empty because they are intersecting at origin, and therefore this L1 union L2. Let us take this is L, that is this set is given as L and this is connected. Moving to the next one, that is again collection of some lines, but this set is disconnected. Actually what we are taking here, we are taking a set here. This is nothing but the line x is equal to a, and this is another line, that is x is equal to b. Obviously what we are taking, a is not equal to b. If we are taking their union, this union is disconnected. Let us see it. So what we are taking two lines. Let us take the first line is this is x is equal to a and this is x is equal to b. What our motive is to justify that this L, this is disconnected. How this is disconnected? Because if we are taking this first part, that is the first one, let us take this as L1 and let us take this is L2. If we are taking H plus intersection this L, what we will get? We will get L1. What H plus is? We have already studied that this is open right half plane, that is this plane. This is actually H plus. So L1 can be expressed as H plus intersection L and L2 can be expressed as this H minus intersection L, and this is left half plane. Meaning is to say that this L1 and L2 both are open in L. Even if we are finding out the complement of L1, that is nothing but L2. From here we can conclude that L1 is open as well as closed. L1 is a proper subset of L and this is non-empty too, and therefore we can conclude that this L is disconnected. because we have shown that there exists a non-empty proper subset of L which is both open and closed, and therefore this L is disconnected. Moving ahead, let us take another example of a disconnected subset of R2, and this is the rectangular hyperbola. Let us denote this set as, let us take this is HR. We are using this notation for this set, which is collection of elements from R2 such that xy is equal to 16. Let us see it. Actually, we are talking about this structure. Let us take this first one is, this is HR plus, and let us take this portion as HR minus. Also note that this we have already studied that this portion is known as H plus, and this portion of this R2 that we have already taken as H minus, and this H plus and H minus both are open in this R2. Now if we are taking the intersection of this HR with H plus, what we will get? We will get HR plus, and if we are taking the intersection of H minus, we will get HR minus. So from here we can conclude that this HR plus and HR minus both are open in this HR. Also, what about the complement of HR plus, that is nothing but HR minus? Meaning is to say that this HR is non-empty. This is a proper subset of this HR. Actually, this is HR plus, and this HR plus is both open and closed. And this itself justifies that HR is disconnected. It is to be mentioned here that we have studied a number of theorems, number of results related to connectedness that were obviously theoretical, but let us see, we have used each and every results at some point to discuss the connectedness of R or the subsets of R, and also we have used to discuss the connectedness or disconnectedness of subsets of R2. Moving ahead, let us discuss about the intermediate value theorem on a closed interval AB, which is well known in calculus. The statement of this theorem is here that if a function f from this closed interval AB to R is continuous, and if we are assuming that R lies between fa and fb, then there exists at least one C in this closed interval AB such that f of C is equal to R. Let us see the statement through graph. So what we are taking a function. Let us take this is the function. This is x is equal to a, and this one is x is equal to b. Let us take this as f of a, and let us take this one as f of b. So what this theorem says that if we are taking any element in between fa and fb, let us take this is R. So we can find out an element C here that is in between a and b such that this f of C is equal to R. One of the well-known example of this mean value theorem is given here. That is, if we are having a continuous function such that fa and fb have opposite signs, then the equation fx equal to 0 has a solution between a and b, and this result has already been used to find out the solution of fx is equal to 0. Let us discuss a general version of the well-known intermediate value theorem in the framework of topology. Even this theorem was the first encountered in the calculus, but after studying this result from the topology, one can see that this intermediate value theorem which we are using in calculus is particular version of the concept from topology, and this concept is based on the theory of connected topological spaces. So the general version of the intermediate value theorem is stated as here: let x tau be a connected topological space and f is a function from this topological space x tau to real line with Euclidean topology. This function is a continuous function. If we are taking two elements p and q in fx as well as r lie between p and q, then r is always an element of fx. In order to prove this theorem, let us assume that this space is connected. Also, this is given to us that this function is continuous function, so we are also assuming it. Now, if we are taking any r which is lying between p and q, note that if p is equal to r or this q is equal to r, then this r will always be member of fx because p and q are members of this fx. So what we are going to take? We are going to take that neither p is equal to r nor q is equal to r. That is, this p is strictly less than r and this is less than q. Our motive is to justify that this r belongs to f of x. Let us try to prove the requirement by using contradiction. So what we are taking, we are assuming that if possible, let us assume that r is not an element of f of x. If r is not an element of fx, then what will happen? Let us take, this is real line, this is r. As per our assumption, p is less than r, also this q is greater than r. If we are taking two sets, one is minus infinity to r and another is r to infinity. Note that both are open in this Euclidean topology, that is open in R. Now what we can take, if we are taking a naught as this minus infinity to r intersection fx, and let us take this b naught as r to infinity, this is open interval intersection fx. What we can conclude from here, note that a naught and b naught both are non-empty as a naught contains p and b naught contains q. Second one, this a naught and b naught are open in fx because topology on fx is relative topology. Also, we have already done such exercise. If we are finding out the intersection of a naught and b naught, that is an empty set, and finally if we are computing the union, that is nothing but f of x. Thus if r is not an element of f of x, what we have shown, we have created a separation of this fx and that is given by this pair, and it leads us to conclude that fx is disconnected. But it is to be noted that what x tau we have assumed, this is connected, and what the function we have taken, that function is continuous. and by continuity of this function fx is also connected, which is a contradiction as from the assumption if x tau is connected and the function is continuous, fx is connected, and if we are taking that this r is not an element of fx, answer is fx is disconnected. Thus r belongs to f of x. That's the proof of this general version of intermediate value theorem. Now if we are taking this x as ab, this is the closed interval ab, note that there is no harm to assume this x as closed interval ab because this closed interval is connected, and in our statement also this x is connected. Also let us take f of a is equal to p and f of b is equal to q. If we are taking these two, then R will lie between FA and FB, and by using this theorem R also is a member of f of x, that is there exists C in x, and which is nothing but this closed interval AB, such that f of C is equal to R, and this was the statement of intermediate value theorem in calculus. These are the references. That's all from this lecture. Thank you.